This conference will now be recorded.
Hello everyone, we are discussing in the last class preparation of alkenes and we will still continue. Two more processes are left for the preparation of alkenes, and once this preparation of alkenes finished, we will see some physical properties of it, and after that chemical properties of alkenes will be discussed. So the first three methods we have seen, and the number fourth method, which is D. Now in this case, starting material will be some alcohol. So starting from alcohol, you will take alcohol as substrate and you will prepare alkene. Now in this case, monohydric alcohol we will obviously take, because if it is more than one OH group, there will be formation of more than one CC double bond. So to keep the factor simple, that there will be formation of only one CC bond, monohydric, that means only one OH group is present, that type of alcohol we will take. And there must be presence of beta hydrogen. Now what is beta hydrogen? Beta hydrogen means, suppose the alcohol general formula if I am writing like this. Now the carbon with which OH group is attached, that carbon is alpha, because with respect to OH this is the first position. Now the second carbon, that will be beta. Now in beta position there must be some hydrogen present. So that is all about the beta hydrogen. The hydrogen which is attached to beta carbon, that is called beta hydrogen. So this type of structure should be there, and here as it is general structure, there may be any substituent. We are not going into the details of substituent, just we are trying to see the general mechanics. Now what type of reagent you will take? You will take mineral acid, concentrated H2SO4, or you can also take H2PO4, phosphoric acid. Temperature 430 to 440 Kelvin. This is one condition that we can apply. Another condition also we can apply, or on passing the vapor of this monohydric alcohol over heated alumina. Heated alumina is Al2O3. Now the temperature is higher compared to the previous case. Now in this case also, one H and one OH will be removed. So it is the net elimination of a molecule of water. Water molecule means what? There will be H and there will be OH. So net removal of H and OH, that is all about this reaction. So here this H will be removed and this OH will be removed. So this sigma bond will be broken, and ultimately you will get CC double bond. So this is the reaction. Fine. Now when there is, that is if the alcohol is symmetrical type of alcohol, that means only not symmetrical, I'm trying to say when there is only one type of beta hydrogen present. In that case, there is no question which one will be major, because you just have one type of beta hydrogen. But suppose there is more than one type of beta hydrogen, in that case there is a question of major and minor arises. The same thing we have also seen in case of alkyl halide, where elimination of HCl HBr is happening, and depending on how many different types of beta hydrogens are present, depending on that which will give more stable alkene. That mechanism also we have seen in the last class, right? So same thing is here. So there is net removal of H and OH, that is you are particularly removing a water molecule. So that is why you can also call this reaction dehydration of alcohol, because it is the net removal of one water molecule, one H unit, one OH unit, and that is the reason this reaction is called dehydration reaction, because dehydration means removal of water. Now if we take here some that is example, suppose we have CH3, simple that is symmetric type of structure you can take. So in this case, see, this is alpha. This is alpha position and this is beta position. Now beta position you have two hydrogen, but you just have one type of beta position, right? So that is why in this case there is a possibility that you will get the alkene like this. So one H will be removed from this carbon. So that is, and OH will be removed. So this OH and one of this beta hydrogen will be removed. So ultimately you will get alkene like this. Fine. But we'll also see example where different types of beta hydrogens will be there. So this is very simple example. You have taken here 2-hydroxy butane, that is the alcohol, monohydric alcohol. Two more examples also you can see. Now we have taken some cyclic type of structure, same mechanism obviously. In presence of concentrated H2SO4 heat, here you have this is alpha carbon, right? So if it is alpha carbon, the beta carbon will be these two. Now though it is beta carbon, but remember both are symmetrical, that is the alcohol is symmetrical in nature. There is only one type of beta hydrogen, so you don't have to choose which beta hydrogen is to remove. You will just get one type of product. So in this case it is cycloalkene. Now the second this is first example, this is second, third example, tertiary butyl alcohol. Now in this case also this is alpha carbon and all these methyl groups are basically beta. So you have total 9 beta hydrogen, and any of these beta hydrogen you remove, you will get 2 methyl propene. It doesn't matter which beta hydrogen you are removing, you will always get product like this. So in these three examples, there is only one type of beta hydrogen. But remember, when there is a chance of formation of two different alkenes because of two different types of beta hydrogen atoms, which one will be more, which one will be preferred? Obviously, the alkene which is more highly, which is more substituted alkene, that will predominate. The same logic that we have already seen in case of alkyl halides. So here we will take one example where you will be able to understand this major and minor product. But the compound must be having two different types of beta hydrogen. So this is a methyl group and this is OH. Now this is alpha carbon, right? This is beta carbon. This is beta carbon. This is also beta. Now these two beta are equivalent type. These two methyl groups are equivalent. Whether you remove any of this hydrogen from any of this methyl group, it doesn't matter. But the two hydrogens that are present here, they will give you a different product. Now, if you remove, let me color it with green, and the color these two, that is these three hydrogens, they are in blue. So this blue, these two methyl groups are equivalent. Now, when you are removing this, any of this blue hydrogen, the product that you will get is this will be the product. Fine. But if you are removing any of this green one, now the product will be, okay, these two methyl groups. Now which one is will be measured? How to decide that? Obviously this will be measured, because in this case if you consider the CC double bond part, you have methyl group, methyl group, methyl group and one hydrogen here. That means total 3 alkyl substituents are there. But in the second case, that is the minor product, there is 2 HH on one side of the CC double bond. Another side you have 2 alkyl groups. So this is more substituted, and that is why this will be the major product. One more example also we can see. Now in this case, we will take some cyclic structure. Remember, cyclohexanol example we have seen in the previous slide. But now I will make this substrate a little different by putting a methyl group here. Now this is alpha carbon, this is beta, this is beta. These two beta are equivalent type, but there is another beta which is this one. So if you are removing hydrogen from this methyl group, that is one H from this any of these 3 hydrogen, and OH obviously you will remove. So the product that you will get is double bond outside the ring. But if you are removing these hydrogens, any of these 4 hydrogens, okay, now the product that you will get is and this will be major. Again the same reason, because it is more substituted. In this case you have 2 hydrogen attached to CC unit, CC double bond unit. So this is why this will be the major product. Fine. So we have seen some examples from when we are making alkene starting from monohydric alcohol. Now the last method for this, that is under preparation heading of alkenes, we have Kolbe's electrolytic reaction. Now, Kolbe's electrolytic reaction, this method we have already applied when we have discussed preparation of alkanes. Remember, there also we have seen how applying this electrolytic reaction we can produce alkane. Now, how to, that is the simplest example that we can start with, CH2CH2. Now, sodium or potassium salt. So here potassium salt is taken. So this is the carboxylic acid, two CO2H group present in the same molecule. And here as it is in the salt form, so it is not CO2H, it is CO2 minus K plus. Now from this, first I will write the net reaction, and once net reaction we will see next individually what is actually happening in anode and cathode, that also we will see. And why it is important, because you may get question like in anode which side product is produced, or maybe the actual alkene that we are our main desired product, it is formed in anode or cathode. To answer all these questions, it is important for us to know that in different products, that is the actual product and the side products, whether they are produced in the cathode or anode, that we have to understand. But first see what is the net reaction. The net reaction is here. This is the alkene that we are getting, and there are some side products, carbon dioxide, KOH, depending on whether you have taken sodium salt or potassium salt, and there is also formation of H2. Next, we will see what is happening at anode and cathode. So at anode, this molecule, that is the carboxylate salt, if 2 electrons are removed from it, now what will happen? 2 electrons are removed, there will be formation of, that is this CO2 part, if it is removed as a neutral molecule like this, what will happen? There will be generation of radical over these two carbons, and when these two radicals are connected to each other, you will get CH2CH2. Fine. Sorry, this should be cathode, because here oxidation is occurring. Sorry, it is fine. This oxidation is occurring here. And what about the cathode? That also we will see. So in cathode, as you know, these two potassium counter ions are still there. Now these two ions, if it is accepting these 2 electrons that is already removed in the anode side, if it is so, now there will be formation of neutral potassium atom. And this neutral potassium atom, in presence of water, because in the medium there is presence of water, there will be formation of 2 KOH and H2. So same type of mechanism we have also seen in case of preparation of alkane. There also Kolbe's electrolytic reaction, this method we have seen. So now, so these two are produced in this side, and KOH and hydrogen gas is produced on the other electrode side. Physical properties of alkenes. Physical state. Remember physical properties of cis and trans alkene, how they differ from each other, that part we have discussed, right? Because depending on cis and trans alkene, suppose same alkene, just difference is in its geometry, 2 geometrical isomers. So physical properties of geometrical isomers we have discussed separately, but this discussion, that is the physical properties of alkenes, that is in general, and we will also compare how it varies with alkanes, that is presence of CC double bond and absence of CC double bond, how it makes the difference. So physical state, first 3 members of alkenes, that means ethene, propene, butene, they are gaseous. Now the next 14 members, so gradually when you are moving to 4th member, 5th member, 6th member, molar mass is increasing, and when molar mass is increasing, van der Waals interaction increases, and that is the reason from gaseous state now they are moving to liquid state. Because when van der Waals interaction increase means what? The intermolecular force between two molecules, that is increased. So they will come close to each other. So that is the reason with increase in molar mass, their physical state is changing from gaseous to liquid. And then after 14 members, when you move to 15 or 16, the remaining alkenes, that is greater than 18 carbon, they will be waxy type of solid, not hard solid, waxy type of solid. They are all colorless, odorless. Only exception is ethene, which is having some sweet smell. Solubility. They are insoluble in water, but are fairly soluble in non-polar solvents. So alkene, just take simple example of the first member. Now there is only presence of carbon and hydrogen. So obviously it will prefer non-polar solvent. But if you consider water, there will be solubility is not possible. Now non-polar solvent, or sometimes it is also called organic solvent. Examples, as you can see, benzene, petroleum, ether. So all these solvents, they are actually non-polar in nature. Ether is also non-polar. If you see the structure, general structure of ether, it is basically non-polar because both sides there is alkyl group. So that is the reason. These are some solvent where it will be soluble, but it will be insoluble in water because it is mainly hydrocarbon. There is only carbon and hydrogen, and as only hydrocarbon means there is presence of carbon-carbon bond or carbon-hydrogen bond. You just have this, but polarity you cannot expect because the electronegativity difference between carbon and hydrogen is not very high. So that is the reason they will prefer non-polar solvent when we are talking about solubility. Polarity. Now polarity, if we compare between alkenes and alkanes, just take the corresponding alkane, which is CH3, and here we have CH2 double bond CH2. If you compare these two structures, what is the difference you have? You have CC single bond here, you have CC double bond here, and when it is CC single bond, it is sp3 hybridized, but when it is double bond, it is sp2 hybridized. Now in sp2 hybridization, S character, percentage of S character, that is obviously high because here 1 S and total 3 P. So S character is only 25%, but in case of sp2, it is 1/3 percentage. That means 33.3%. So as S character is high, the polarity, that is the electronegativity of this carbon, when it is sp2 hybridized, that is high. So there will be comparatively you can expect some dipole-dipole, but that is very weak dipole-dipole interaction compared to the sp2 hybridized carbon in case of alkane. Now because of this sp2 hybridization, comparatively there will be some weak dipole-dipole generation. So polarity, in terms of polarity, we can say alkenes are slightly more polar than alkanes. Boiling point. Their boiling point increases regularly with increase in molar mass, and that is along the homologous series. So suppose you have ethene, then you are moving to the next one, which is propene, then you are moving to butene. So gradually there will be increase in the boiling point, and that is by the amount 20 to 30 Kelvin for addition of each methylene group. So for example, when you are moving from C2H4, then you are moving to C3H6. So in this case, if you see the boiling point, the corresponding boiling point here, it is 104 degrees centigrade. There is a negative sign. But for propene, when you have added one CH2 group, now there is difference. So the boiling point is increased around, you can see around 40. So 20 to 30 Kelvin or near about 40, there is increase because of addition of CH2 group. Now compared to alkane, that is like alkanes, straight chain alkenes have high boiling point compared to its isomeric branched alkenes. So the same thing that you have seen in case of alkanes, that also you can see here. Now we can also write the boiling point for the corresponding alkane so that you can compare. So C2H4, but now I will write C2H6 and C3H6, that means 3 carbon, the corresponding alkane is C3H8. Now in this case, if you see the boiling point, it is minus 89 degrees centigrade and this one is minus 42 degrees centigrade. So here you can see, if you simply compare, that is keeping carbon number same, if you compare minus 89 degree and this is minus 104 degree. So it is slightly lesser. I mean to say C2H6 is slightly greater than the boiling point of C2H6. Now, explanation that you can give here, 2 hydrogen is basically less compared to C2H6. So there will be slight difference in molar mass, and because of this difference, there a boiling point increase, slight increase that we can expect. Same thing also here, minus 42, minus 47. Keeping carbon number same, but see here 2 hydrogens are extra, so molar mass is slightly high. So you can expect boiling point to be slightly increased. So that is the value for boiling point. Next you will see melting points. Now for melting points, alkenes depends on the packaging of the molecule. Remember, in case of cis trans, we have seen that in cis it is not very symmetrical, so packing is not very good. But in case of trans, because of this symmetric nature, it is packing is better. But that is the melting point comparison for geometrical isomer. But if we see compare alkene and alkane, the melting points are not very different from each other. So here again we can write C2H6 and C3H8 melting point. C2H6, it is around 183. All are will be negative because they are after all gas, and this one is now just compare with C2H6, that is a corresponding keeping carbon number same. So C2H, if we see it for 0.4 degrees, C3H6. So see, if you compare again, it is they are not very highly different from each other. This is around minus 170, this is minus 183. So there is not much correlation that you can say, because their values are not drastically different. And in this case, the boiling point is slightly high, but here it is slightly less. So don't try to draw any conclusion. You can say that they will be having more or less similar type of melting point. Fine. Let me check. C2H6 minus 183, C3H8 minus, yes, it is correct. Now we will start chemical properties of alkenes. Now under chemical properties of alkenes, this is going to be very, large amount of discussion will be there, because in case of alkanes, you know, there is no CC double bond, only CC and CH bonds, and those bonds are very inert in nature. They do not like to take part in reaction. But now when you are talking about alkenes, because of this presence of CC bond, now you have one extra pi bond, which you have not seen in case of alkanes. Now because of this pi bond, you can expect more reactivity compared to alkanes, because pi electrons are loosely held, they can easily take part in reaction. So that is why the chemical properties of alkenes are very versatile compared to alkanes. So there will be many different types of reactions, especially you will see under the type of addition reaction, where some small molecules will be added to the alkene. Under this heading only, addition, you will see 5 to 6 reactions. And then we will start oxidation of CC double bond. Because of this pi electron cloud, they can be, that is in presence of some good oxidizing agent, these pi electrons can be easily captured by them. And then there is very special type of reaction that you can expect from CC double bond. that is you can extract from alkenes, that is polymerization. So under addition there will be 5 to 6 reaction. Then under oxidation also, depending on what type of oxidizing agent you have taken, there will be different types of reactions. And then there is polymerization. So they are more reactive than alkanes because of CC double bond. Typical reactions of alkenes involve addition of an electrophile across the double bond. So this is the most important type of reaction when we talk about chemical properties of alkenes. There is a first one, the type addition. And you know, in addition what happens? That is general way. If I say this pi bond will be broken, and when this pi bond is broken, 2 units will be attached. It may be, suppose in general I'm writing the reagent is AB. So there will be formation of 2 new sigma bond and the original pi bond is broken. Fine. The first type is addition. And why we are calling it electrophilic addition? You will always see it is called electrophilic addition. There is also nucleophilic type of addition for alkenes, but that is not very common. Common is electrophilic addition. Why it is so? Because when there is pi electron cloud and you have in the medium some electrophile. Now the electrophile directly you can use, or the electrophile can be generated from the reagent. So suppose from this reagent you are generating the electrophile A plus. Now if this is the electrophile E plus, we write electrophile like this, then this part must be reacting as nucleophile. So electrophilic addition, the term that we are using, that is based on the fact that the reagent is electrophile. So if the reagent is electrophile, obviously the main substrate, which is alkene, that must be nucleophilic in nature. Why it is nucleophilic? Because it has pi electron density, which it can donate to the electrophile. Now, which electrophile? That depends on what type of reagent you have taken, depending on the reagent type AB. Though there is, it is not that there will be always that is positive charge containing species you will always get in free condition. That is not the case, but still there will be, we call this reaction as electrophilic addition reaction. So here alkene, which is nothing but the nucleophile here, that will be attacked by some electrophile generated from the attacking reagent. The pi bond of alkene is broken and there will be formation of 2 new sigma bond. Under the heading of addition, the first reaction that we are going to see, hydrogenation. That means addition of the simple molecule H2. Now this reaction you have seen, because when we add hydrogen to CC double bond, obviously you can consider this HH as if one H plus is generated from H. So that is actually our electrophile, but whatever it is, ultimately you will get some alkane. Now this method, where we have seen it already, we have already seen it under the heading of preparation of alkanes, because this reaction we are discussing under the heading of chemical properties of alkanes, but this is also the preparation method of alkane, and there we have already seen this reaction. Just we'll brush up quickly. Hydrogen adds on to alkenes in presence of some metal catalyst to yield the corresponding alkanes. Now this is known as catalytic hydrogenation. Because hydrogenation, why? Because addition of 2 hydrogen atom. And why metal catalyst we are using, so that is why it is called catalytic hydrogenation. In presence of some metal catalyst, nickel, palladium, platinum, we are doing this hydrogenation, and that is why the name is such. So this is the number 1, addition of H2. We are not going further details because we have learned this. The second one is addition of halogen, or you can call it halogenation. In case of alkane, when we have seen halogenation, we have already seen the radical mechanism, but now it is not so. It is not radical mechanism. So when alkene is treated with halogens, now mostly this is observed for chlorine or bromine, not iodine or fluorine, because fluorine is very much reactive. That is the problem with fluorine, and iodine, the problem is it is not very reactive. So mostly the reactions that we'll see, it is from chlorine or bromine. Now what we get? We get 1,2-dihalo alkane or vicinal dihalide. So you have started with alkene. There may be any 4 substituent. We are not going into the details. You have added the halogen. I have here written X2. X2 means the general way of writing Cl2 or bromine or iodine. Pi bond will be broken and there will be 2 new sigma bond, CX bond, CX bond. And it is also called 1,2-dihaloalkane because their position with respect to each other is 1,2. It is also called vicinal dihalide. Remember, there is another term, geminal. Geminal means where same carbon is containing X, and that is called geminal or gem. But this is vicinal or vis, which is when their positions at 1 position and 2 position. Okay. Now in this case, that is F2 and I2 are not synthetically very useful. You can do the reaction, but the problem is when you take F2 as the halogen, the reaction is so explosive, so reactive reagent that you will end up with mixtures of so many products. That is, side products will be so high, it will be difficult for us to isolate the actual desired product. And the problem with iodine is that it doesn't proceed to significant extent. There is a possibility that it will move towards the reactant side again. That is the problem we face. Now, in this case, one more thing, interesting thing is that this reaction can be used as a test for determining unsaturation. And that you can do only with bromine water, because bromine water, it has a specific color, which is reddish brown type of color. And when you are suspecting that your organic sample may contain some CC double bond, not just double bond, it may be triple bond also. So that is why it is mentioned here as unsaturation, not just CC double bond. But now we are talking about alkene, so let's focus on it. So bromine water, which is having some specific visible color is there, and your sample, you just want to know whether CC double bond is present or not. So if the color is discharged, because when BR-BR bond is broken and there will be two newly generated CBr bond, obviously the color will not be present anymore. So it is something like this. So if your sample is alkane, the color will be still present. So there is no change in reddish brown color. But if the sample contains CC double bond, now the color will be gone. Now why it is so? Because this bond is now broken and there is formation of CBr bond. So that is why the color is discharged. Now here, if we talk about mechanism, we can be tempted to write the mechanism like this. How? We can write it like as if the first halogen is attached and that is a negative charge, it is as if captured by X, and you can also write here as if del plus and del negative, that means partial positive charge and negative charge, because we have not broken it fully. Now if this X is attached to one of these carbon, another carbon will have some positive charge, and then next the remaining part is added. But actually this is not the correct mechanism. There is no formation of carbocation. Okay. Now if there is no formation of carbocation, what is actually happening, that we have to understand. Fine. So there is anti-addition, and also we have the proof for this anti-addition. Now what is this anti-addition and what is the proof? Now if we want to understand it, let me write the actual mechanism, because this is not the correct mechanism. Now the actual mechanism, if we see, in presence of this halogen, you can write the halogen like this. Now there will be first some interaction of this pi electron cloud and this one of this X. Now when this is so, there will be some electron displacement. That is the electron pair that you have. As this pi electron, it is attracted towards one of these halogen terminal. So these two electrons will be shifted to the other terminal, and this part is now will be attached to this CC double bond unit like this. And this type of ion, obviously it will carry some positive charge. It is called halonium ion. Now general term I am writing here halonium. If it is chlorine, then it is bromine, it will be bromonium, chloronium like this. So this type of ion will be formed, 3-member type of ring. But this is obviously not very stable and it will be immediately attacked by the other part which is already remained. And that X minus, it can either attack at the left hand side carbon or it can attack at the right hand side carbon. But see, if there is similar type of substituent present at these positions, suppose you have substituent all are similar, all are hydrogen or all are methyl, then there is no question of selectivity whether X minus will be attached to this side or this. But depending on that is sorry, what I'm trying to say, yes, depending on the substituent it may vary. So this is one point, and another point is that one point, just try to see. X minus, when it is symmetric, actually ultimately the result doesn't matter because you are adding 2x unit, so it is symmetrical. That is the reagent. If the reagent is type of AB, then the question of selectivity arises. But here the reagent is AA type because both are similar atom. So that is why this type of question doesn't arise. But the problem is the thing that is a proof of anti-addition. It means what? The proof of anti-addition means that this X minus is added from the opposite side of this halonium ion. Because this side you already have this type of 3-membered ring, that is CXC. So obviously the X minus, it will be attacking from the anti side and it can attack at any side. But important point is this is anti-addition. So there is two steps. First, there is formation of this halonium type of ion, and the second step is where the X minus is attached to it. And here the question of that is selectivity, that is carbon number 1 and carbon number 2. Even if they are containing different types of substituent, there is no question of selectivity because ultimately it is the same unit is adding. But remember here anti-addition, that factor is important because if you consider the previous mechanism where free carbocation is generated, if you consider that mechanism, then the question of anti-addition does not arise. Because in that case, what we have seen? We have seen that CX is here. Positive charge, positive charge. So X minus, it can attack from this side or from this side. That is from the side of CX bond or from the opposite side. But when it is this type of halonium ion, obviously one side is blocked. So the X minus, that will be attacked from the other side. Fine. Now the proof is, when we start from Z-butene, we get racemic mixture of products. And when we start from E-butene, that is, you can also call it trans, then we get this type of compound. And here it is not racemic mixture, it is a single compound. And what the full, that is R and S nomenclature is written 2R, 3S, 2,3-dibromobutane. Okay, that is one carbon will be 2, another carbon will be 3. Now, how it is, how we can say that this type of anti-addition is only giving you this type of reaction. So when you start from cis, you are getting racemic mixture of 2 products. Now look at the 2 products, 2s, 3s. That means if I am writing here 2 and 3, so obviously its enantiomer will be RR. So 2s, 3s, if it is the nomenclature of one product, another product will be 2R, 3R. And here if you place a mirror, you will also be able to see these two are mirror image to each other. Okay, so this is racemic mixture. Now go to the detailed of it. So as I have said that halonium ion is first produced. That is the first step, formation of bromonium ion. In this case, bromine we have taken, so that is why we are calling it bromonium ion. And this type of bromonium ion is generated, and the rest of the part of the reagent is now Br minus. Now this Br minus, second step is, this Br minus is now attacking to the bromonium ion from the opposite side. That is why it is called anti-addition. If you follow the red arrow, you will get this second product, this product. From the color you can itself understand. And if it is attacking at the blue, because the chance of addition of Br to both sides, it is equal, because both sides it is same. So that is why both these product will be generated in equal amount and you will get some racemic mixture. So one form will, that is if you consider rotation of optical rotation, so it will cancel each other because they are racemic mixture. Now if you consider the free carbocation type of mechanism, obviously you will not get this type of product, because in that case, as I have said in the previous slide, because now that chance, let me write bromine here. So there is positive charge. Now Br minus, it can attack from both sides. But when it is bromonium ion, one side is blocked. It will just attack, it is just bound to attack from the opposite side. But that is not the case if it is free carbocation. But free carbocation is not the mechanism. And in this way, we can prove it. Now, what about the mechanism for the trans isomer? So when it is trans isomer, again cyclic bromonium ion we are getting. This is cyclic, right? Now Br minus, it can attack from the opposite side. Now if you follow the red or blue, ultimately you will see both these compounds are actually same compound. Now I will also show you in the next slide how these two are identical. It is actually 2R3S, but how it is so, that we can understand. Fine. Now one term you have to know here, stereospecific reaction. So stereospecific reaction, we call those reactions where a particular stereoisomer of the starting material, for example cis or trans or E or Z. So when you have same substrate, only the difference is one is cis, another one is trans. That means you are using a particular stereoisomer. Either you have started from cis or you have started from trans, not mixture. So when there is a particular stereoisomer present as the starting material and you are getting a specific stereoisomer of the product. So here what is happening? From Z you are getting racemic, from E you are getting single product which is identical. That means it is fixed. So if you are getting if you already know the product is racemic mixture, you can easily predict that your starting material must be Z butene. So there is some selectivity, and these type of reactions are called stereo-specific reaction. Because when you have started from Z butene, you will always get racemic. You will never get identical. Now this is a term we use for this type of reaction. Okay, so next slide you can see this is the mechanism, but it is generated from which one? It is generated from the cis or Z. This is generated, right? And in this case, you can easily understand the mirror image relationship. And also you can, when you will put S or R nomenclature, that is another way to understand that these two are enantiomer to each other. But the second picture that you are seeing, that is generated from trans. So you are getting this from trans. Now, if you are having some trouble to understand how these two molecules are same, you can also convert it to sawhorse. Right? In that, also you will be able to understand. So if I am converting it to sawhorse, suppose you are looking at the molecule, your eye position is somewhere here. So if you are looking from this side, methyl, and if you do the same thing here, H, again you are looking from this direction. Now it will be H, Me, Br, methyl, back, and this is hydrogen. Now, if I rotate the molecule, see what I'm trying to say by rotate. The back carbon, if I'm changing its position like this, now what you will get? You will get the front carbon I am not disturbing. Actually, you can also do RS nomenclature. That way also you will be able to understand whether it is same molecule or not. So why I am rotating this molecule? Because only in this way you will be able to understand that there is a sigma plane present. If you cut the molecule along this point, you will see both half are actually same. So there is internal plane of symmetry. And when there is internal plane of symmetry, that means this compound is nothing but meso. And the same thing you can also do from the other molecule. If you rotate this front carbon, keeping the back carbon same. So back carbon I am not disturbing, and the front carbon, now Br is up. H methyl. Let me check once more. Sorry, it will be methyl. So when I have converted from this, methyl is this side, H is this side. So methyl will come here and H. So here also you can see if you cut the molecule in the this CC bond, if you cut to the middle part, there is internal plane of symmetry. And here methyl here, hydrogen is here. Now just focus on these two molecules. It seems as if these two are mirror image to each other, because HH towards this side, and for the other molecule H and H towards the, as if just mirror image to each other. But don't think it is mirror image, though there is mirror image relationship, but actually there is internal plane of symmetry. So when there is sigma plane present itself in the molecule, we cannot say that this is optically active. This is not actually optically active because of this internal plane of symmetry. Though here it is written as 2 or 3s, but because of this internal plane of symmetry that you can understand after converting it to Sohers easily, it will help you to understand how the internal plane of symmetry present. So ultimately it will be identical or meso compound. And as it is not optically active, no question of getting enantiomer. Now how to remember this easily? There a simple thing I can say, as the mechanism is anti-addition. So whenever you have some mechanism where two units are added from the opposite side, because another way to add two units is from the same side, which we call syn addition. But in this case, it is not syn addition, it is anti-addition. So when it is anti-addition and your starting material is cis, right? So when it is cis and you are combining with anti, your product will also be two different. But when it is trans starting material and you are combining it with anti mechanism, that means trans already anti groups, you are doing another anti mechanism. So as if these two are cancelling each other, and ultimately your product will be some optically inactive. So this is just a simple way to remember. Similar thing we'll see when it is syn mechanism and you are starting from cis. Now you will get identical compound. But when it is syn mechanism, your starting material is trans. These two will not cancel each other. Ultimately, you will get racemic mixture. But in our case, this is the anti-mechanism. So from cis, you will get racemic mixture. Or if it is trans or E, you will get single compound, which is meso. Now, the next important information, suppose the reaction, it is normally done in what type of solvent? We do this reaction in organic solvent like CCl4 or dichloromethane, CH2Cl2. Now, these cannot, and that is sometimes what happens, the solvent molecule itself can take part in the reaction, but that we do not want. We want only, we will take some alkyl, we are using X2, and what we want 2X to be attached to this carbon. Solvent we use, that is fine, but our purpose to use solvent is not as reagent, because if that is happening, we are not getting our desired product. So it is just a solvent. So this type of solvent are normally used, or CH2Cl2, and they will not interfere in the reaction. But if you do this reaction, suppose you are doing it in presence of water. So same reaction when you do in presence of water, and obviously the reagent is there. Now what will happen? This water, the HO part of water, it can also that is make some different types of products, and that is the problem we have to face in this reaction. So here CCl for DCM is used because they cannot act as nucleophile when the halonium ion is formed. But if you take, by mistake, if you take carried out in water, for example, halohydrin is formed by the addition of water to the halonium ion. So in this case, what happens? There is net addition of X from halogen, obviously, and OH will be added from this. So this type of compound is called halohydrin. It is not halogenation reaction. It is a different compound we are getting, halohydrin. So this part is coming from water, but that is obviously the undesired product. Now, though we are saying it undesired product, but suppose if you actually your intention is to make halohydrin. Suppose you do not want to make this product. You want to make halohydrin. Then you can use water as the solvent. That is purpose. Our purpose when is to make this. Now that makes another type of reaction which we are now going to discuss, and this is number 3. Addition of hypohalous acid. Hypohalous acid means HOX. It may be HOCl, it may be HOBr. So when your purpose is to make halohydrin compound, remember which one is halohydrin? This is halohydrin. Halo is from X, hydrogen part is from OH. So when your purpose is to make, so you can either use directly HOX, HOCl, HOBr, or you can use mixture. See, now this you have just seen in the previous slide, isn't it? That is X2 if you have taken in the solvent water. So that is actually now the reagent. So in this case, alkenes undergo electrophilic addition reaction with the hypohalous acid. Hypohalous acid is the general term. Sorry, it will be HOX, not HX. HX is HCl, HBr. It is HOX. That is the general way to write it. Such as hypochlorous acid, which can also be produced from the reagent combination chlorine and water. Now here addition occurs according to Markovnikov's rule. Now what is Markovnikov's rule, which is applicable for unsymmetrical? That we will discuss separately. Here just focus on the reagent. We either use HOCl or HOBr and we get halohydrin. Now suppose you have taken HOX. So what will be the mechanism with HOX? So when it is HOX reagent, now we have started with so here the mechanism is first from the Cl, better I write in general way, from HOX. See, in HOX, if you consider electronegativity, oxygen is obviously more electronegative than X. So this part will be as if the negative part, and this part will be as if the positive part. And the positive part is actually electrophilic addition. And as this is electrophilic addition, this pi electron density, it will be attracted towards this positive part. And as a result, first you will get CH2X and there will be positive charge. Or actually better, there is no free carbocation. It is mostly like the halonium ion, like this. Now there is positive charge. In the second part, now there is in the medium HO minus. This HO minus, it can attack here. Now there is a chance of selectivity. If that is HO can also attack to the other carbon, I mean this way. But the dotted arrow that I have just drawn, that is not very, it will not give us the major product. And why it is so? That is actually based on Markovnikov rule, which is applicable for unsymmetrical alkene. Now, this alkene is propene, and this is unsymmetrical, isn't it? Now the question of unsymmetrical symmetrical arises, because in the previous reaction, which is addition of x2 is symmetrical, 2x symmetrical, but now you are adding HO and X. This is not symmetric. That is, two different parts are coming from reagent. So now whether you take unsymmetrical alkene or symmetrical alkene, that factor will be important. And to understand which one will be giving you major product, that can only be understood from Markovnikov's rule, that next day we'll discuss. Today we are just seeing the mechanism. So finally, if you follow this arrow, water, that not water, OH will be added here, and here we are getting CH2X. So this is the mechanism when it is starting from HOX. But you can also do it starting from X2 and H2. So indeed, X2 and H2O. Again, you can write, okay, the mechanism is already there. So now we have taken chlorine in presence of water. The first addition is electrophilic addition, where one chlorine part from chlorine molecule, it will be acting as E+, that is the electrophile. This step is slow, and once this halonium, this type of cyclic halonium, or better you say chloronium ion, is formed, now water will attack from the opposite side. So same thing you have also seen in the previous mechanism. That is when it is HOX. But it will be opposite addition or trans addition, you can call it anti-addition, because this side is already blocked. And water is added. Now oxygen is positively charged. Another neutral water molecule can take this extra hydrogen, and ultimately you are getting OH and Cl. Now here, what is Markovnikov? Just I will say as simply as possible, because details of Markovnikov we will discuss in the next class. It will take some time. Here, Markovnikov's rule, it basically says when you have any reagent, suppose unsymmetrical reagent AB type, and in this reagent, depending on electronegativity, one will be generating the positive part, another will be generating the negative part. So suppose here if B is more electronegative, it will generate the negative part, right? And when you have unsymmetrical type of alkene, now see carbon number 1 and carbon number 2. Carbon number 2 is having more hydrogens attached to it. Carbon number 1 is attached to less hydrogen attached, because only one hydrogen, here two hydrogen. Now Markovnikov rule says that when you have this type of unsymmetrical reagent, AB, one part will be positive, another part will be negative, and you also have unsymmetrical alkene. Now what will happen? The negative part will be attached to that carbon which is having lesser number of hydrogen, and the positive part will be attached to that carbon which is having higher number of hydrogen. Now the same thing you have already seen here. So in this case, this is carbon number 2, this is carbon number 1, and 2 is having more number of hydrogen, and that is the reason ultimately this positive part, because HOCl, obviously this part will be positive, oxygen is more electronegative, so the negative part is attached to that carbon originally, which is carbon number 1, and that carbon is containing lesser number of hydrogen, and the second 2 number carbon is containing higher number of hydrogen. So this is all about the Markovnikov rule. Details of it we will see in the next day, and which will be discussed in detail for addition of hydrogen halide. That is how you can add HX. So we will end the session here. Thank you for listening.